class, I wanted to go ahead and talk about the last couple examples that we didn't get a chance to go through very thoroughly at the end of class. Make sure that I address these more fully and definitely hopefully get any confusion cleared up that you guys may have about these. So we ended talking about division of complex numbers, and we saw this example A, which is when you have a complex number divided by another complex number, and you have to use the complex conjugate of our denominator to get rid of the I, essentially, in our denominator. So here was 4 plus 3i, so we did 4 minus 3i. So the principle and the idea behind that is the same for something like B. Here, I just happen to have a pure imaginary number, and the issue is still the same. I can't have I left in my denominator. So how do I get rid of I? I'm going to use my complex conjugate. So the complex conjugate for positive 6i is negative 6i. And essentially, if you're thinking of complex conjugates, they have the same real and imaginary part. Like in our previous example, they both shared the real value 4 and the imaginary value 3. However, the sign of the imaginary part, one will be positive, one will be negative. That's still the case here, except we don't see the real part because it happens to be 0. So 6i is really 0 plus 6i, and its conjugate would be 0 minus 6i. So I want to multiply really this fractional imaginary value by the conjugate of our denominator, which is negative 6i. So when I do that multiplication, on the top of my fraction, I'm going to have negative 4 plus 5i get multiplied by negative 6i. And then on the bottom, I'm going to have positive 6i multiplied with negative 6i. So on the top, we have a pure imaginary number, or a monomial kind of looking thing, this negative 6i, multiplying to a binomial or complex number. So how we handled that in the past was we distribute, and that's still the case. So I'm going to distribute my negative 6. So negative 6 times our 4 is going to get me 24, positive 24. I, because our 6i has an I on it. And then 5 times our negative 6 gets me negative 30 I squared, because we have an I times an I. Then on the bottom, normally I try and simplify kind of the numerator and denominator separately. In this case, the denominator isn't really that much extra work, so I feel confident that I can do it and not make any mistakes. So we can deal with the denominator or just save it for later. That's okay too. So negative 6 times 6, that's negative 36. And then I times I is I squared. And so now we need to replace anywhere I have my I squared with its equivalent value, which is negative 1. So what am I going to have here? I'm going to have 24i minus 30. Instead of I squared, we write negative 1. And then we want to simplify this. So 24i will stick around. This will be turned into a positive 30 and a positive 36. So I actually have to write the positive sign there. Just leave it as 36. So from here, really we just need to clean this up and get it into the standard form. Right now it's definitely not in the standard form because my I unit is not at the end. So I could reorder on the numerator, make this 30 plus 24i, all over 36. And then what we saw like in the last example, this really isn't the standard complex form because I can't identify the real and imaginary components of it. So what I need to do then is go ahead and divide each of these separately. So 30 over 36 and 24 over 36. And anytime you have a fractional value, no matter where you see it, we always want to try and reduce. So 30 over 36, I do believe, have a common factor. So you can, look at the factorization and see kind of what they may have in common. Or the other thing that I mentioned to you guys is that pretty much all the calculators have the option to change decimals back into the fractional form. And when it does that, it will also reduce it for you. So here this would reduce to 5/6 because there's just a shared factor of 6 on the top and the bottom. And so if you don't know how to do that in your calculator yet, that's definitely something to come ask me about because it really is helpful, especially when your fractions get into kind of larger numbers. So 24 divided by 36, again we can look for whether or not these reduce. I can tell you right now this one does, to 2/3. And that would be our value in standard form with the reduced fractions. Now we also want to look at higher powers of I, not because you guys will probably see it, but you may run across it, and we want to know how to handle these cases. So I is really the only unit we want to keep around. If I have higher powers of I, we want to change them. So like I squared, we changed it into -1. If I saw an I cubed or I fourth or any higher power of I, we would also want to do that conversion. Well, how do I handle that? So if I had like an I cubed, I could break that down as I squared times I, where I squared turns into a -1. So this turns into a -1 times I, or a negative I. I did the fourth, we could break down as I squared times I squared. Each of those turns into a -1. When we multiply, we get a +1. And so there's really, what the process we're going through is breaking these down into powers of I that we know already. So like breaking it down to an I squared or just an I. And what's really interesting is that we essentially cycle through the same 4 values. I'm going to have an I, then a -1, then a negative I, then a 1. When I go into power 5, 6, 7, 8, it's the same pattern. I, -1, negative I, 1. So then if I went to the next 4 powers, it would follow the same pattern. I the 9th is I the 10th is -1, I the 11th is negative I the 8th would be, or I the 12th would be 1. So we're always cycling through those same 4 options. So it's not necessary, really. I mean, you could break all these down into I squareds multiplied by themselves a certain number of times with an I multiplied potentially. Or you can just know where you land in the pattern. So that's one option too. So here we have the first 12 powers of I. Should you ever need a higher one, you could just go back through the same 4 values and figure out where you land. Are you the I, are you the -1, the negative I, or the 1? So these will always repeat every 4th power. And then the last thing I wanted to do was comment on the fact that we can have quadratic equations with a complex solution to them. And we saw these in the past. We've run across them, but usually what would happen is we get down to, like, say I'd have a square root of a negative number, right? And we would stop and say not a real solution. And that's true. Those aren't real solutions, but they are solutions. They just happen to be complex values. So we want to know, now that we have learned about complex numbers, how do we write those as complex numbers? So if I look at this quadratic equation, x squared plus 2x plus 7, I might try to factor it. However, there's no factors of 7 that would add 2. All I have is 7 times 1, which to create the positive 7, all I could do is positive 1 and positive 7, and that would get me 8, not 2. So this guy's not factorable. He also doesn't fit the pattern for the square root method of solving quadratics because I have an x term and an x squared. My variables are not all being squared there. So that's out. So I could either complete the square on this, or I could use quadratic formula. Of those 2 options, quadratic formula is probably the most approachable for pretty much all students. So that's why I tend to default to that with you all, because I know that tends to be the preference for most students. But you could also use completing the square, and that would be fine. So if we are going to use quadratic formula, we need to identify our A, our B, and our C value. And let me actually do that in different colors for you. So let's look at A. So A is going to be the coefficient of x squared. In this case, it's 1. B is going to be the coefficient of x, which is 2. And C will be our constant term, which is 7. And then we also want to write down our quadratic formula before we use it, so the reader knows what we're doing to all our values, why we randomly did all these operations. It's because we're using a formula. And it also helps us remember it the more we write it down too. So now I can go ahead and plug in my A, B, and C values, and then start calculating them in this formula. So A was 1, B was 2, and C was 7. Okay, so here the suggestions I had for you guys were to kind of clean it up a step at a time. So I cleaned up the minus b part in the denominator. We can do 2 squared, which is 4, and then figure out this piece of the three values being multiplied and what sign that should be. So it's a negative times a positive times a positive, so it's negative. 4 times 1 is 4, times 7 is 28. And what we want to do from here is go ahead and reduce what's inside our square root. So let's see what that becomes. So this would still be negative 2 plus or minus. If I take 4 away from my 28, that's a negative 24. And I need to reduce that root now. So in the past, we would have stopped right about this point and said, not a real value, which it's not, it's complex. But now we can handle that complex value part. So I would want to go ahead and simplify that. And let me actually do that off to the side. I think that might be helpful rather than writing it out, this reduced square root several times. So if I wanted to reduce the square root of negative 24, we would break it up as the root of 24 and the root of negative 1, so that my square root of negative 1 can become an I. And then 24, we want to go ahead and reduce that root. So what are we looking for? We're looking for two factors that would essentially be a square that we could pull outside of our square root. So I'm looking for 2 of the same factor. So here I'm breaking down my 24, and I do have 2 of the same factor. I have a double set of 2's. So I'd be able to pull out the 2, and then 2 times 3, these leftover single value factors would stay inside. So when it's all said and done, that's 2 root 6i. So that should go where our square root is, 2 square root 6i. So we just did that off to the side. Okay, then here we would want to reduce our fraction if possible. Since I have a common factor of 2, I can go ahead and reduce that. So negative 2 divided by 2 gets me a negative 1. The 2 out in front of my square root can also reduce with the 2 that's in the bottom. So 2 over 2 is 1 times the square root of 6i. So those would be my complex solutions. And another thing that I think is neat to point out is there are 2 solutions, right? Negative 1 plus root 6i and negative 1 minus root 6i, which those are complex conjugates. And that's a very helpful thing here that we can kind of pick up on, is that if we're solving a quadratic equation and get a complex number, that the complex value that comes out will always be complex conjugates of each other. And that's going to be kind of more important later on when we deal more with polynomials, but that's kind of a powerful thing, is that we'll automatically get conjugates. These solutions have to occur in those conjugate pairs.